So we'll continue with actually a pair of talks. First, part one of a coaction for Feynman integrals by Claude.
Okay, thank you very much. And let me, of course, first thank the organizers for giving me the opportunity to speak. Yeah, as David already said, it's a pair of talks. It's some work that was done in collaboration with these people here. And Ruth Brito right after me, and she will give the second part of the talk. So let me first introduce the topic. And sorry, there seems to be an issue. Yeah, okay, now it is. Let me first introduce the topics. So I guess we all agree that Feynman integrals are kind of the cornerstones of what we would call perturbative QCD. Those are the things we need to compute. And therefore, we want to understand them as well as we can. So the kind of questions you can ask yourself then is, well, what does it mean you want to understand them as well as we can? Well, for example, what kind of functions do we get when we evaluate them? And if we understand the class of functions that we get, maybe there's some hidden structure behind these functions that we would like to understand better. And to get a feeling for that, well, let's first recall that in many cases, Feynman integrals evaluate two polylogarithms. You've seen them already in other talks. I don't need to spend too much time on the definition, but I recall it here. So a polylog is an iterated integral. So there's an iterative definition where you just essentially integrate more and more dt over t minus something. So at weight 1, so if you do one integration, you get just a log. If you do two integrations, well, you can get a product of logs, or you get a dilog, which I guess many people know from one-loop calculations. But of course, now you can continue and you generate more and more functions. So those are kind of the prototype functions that you get when you compute Feynman integrals. But let me also mention that we know that while this is true at one loop, or that's what we expect, beyond one loop, we know there are other functions that show up, but that's not what I will talk about here. So I will focus here on Feynman integrals that evaluate two polylogs. Okay, so polylogs are kind of the stereotype functions that you get for Feynman integrals. So if there is some kind of hidden structure for Feynman integrals, it must be also manifest in the polylogs. And while there is some more structure for polylogs, because polylogs are actually, if you evaluate them, they give you not just any number, they give you a certain class of numbers that is called periods. And indeed, periods, we know from the work of Francis Braun, are equipped with what is called a coaction. There's some algebraic structure on them. And well, the coaction already appeared in Lance's talk. It's actually the same quantity. But let me recall you what it is and show you the formula of how it is obtained. So the coaction delta acting on some polylog gives you, roughly speaking, I'm sweeping in many technical details on the carpet, it gives you a linear combination of terms. Each term is a pair, and a pair is noted here by this tensor symbol. And the first entry in this pair is, again, a polylog, but where you see here the vector of singularity, so that's where the poles are when in the integrand. Here I just take a subset of the poles. So I do the same integral, but only with a subset of the poles. I get an iterated integral with fewer integrations. And in the right factor, what I need to do is, well, I keep all the same singularities, but I now integrate over a different integration contour. I choose a different contour. For example, if A has singularities, the vector of singularities are A1, A2, A3, A4, then GBA would be integrate the differential form, which has superposed these positions along this contour here. You start from 0, you go to A4, take the residue at A4, then integrate from A4 to A3, take the residue at A3, and so on and so forth. So that is a way to represent the coaction. Now, experts probably know that it is a bit more complicated. This thing should be what's called the RAM period, but let's not go there. Let's just think of them as real functions. Okay, so another way to look at it is the following way. So let's take this thing a bit apart. So I said that here, I sum over objects that have the same integration contour, but I take a subset of singularity. So actually, what I do is I have here an integral from 0 to z of an integrand with singularities in certain places. Now in the first term, I take the same integration contour, but only a subset of singularities. So this smells very much like a sum over master integrals, where you have here the propagators, A would be the position of the singularity, so the propagators, and here you have all possible integrals with fewer propagators, so this would be all the subtopologies. And then in this factor, well, I have the same differential form, but I change the contour. And this contour, you can think of it for now, a bit in a sloppy way, as being dual to the differential form omega b. So this is the differential form that has poles at the locations b, while this is the contour which corresponds to taking the residue at the positions b. So in that sense, there's kind of a duality between omega b and gamma b. Okay? And so the first question would be, okay, can you write down a similar formula than this one here for polylogarithms for other classes of integrals? And on top of that, well, maybe also for Feynman integrals, or at least for certain classes of Feynman integrals. And that something like this should exist, we know from the work of Francis Brown, who has shown that actually the motivic coaction naturally acts in Feynman integrals. But here we want to have some very concrete representation, in particular also in dimensional regularization, because we usually know the Feynman integrals diverge and we want to regulate them in some way. And a good way to do that is dimensional regularization, where you take as the dimension 4 minus 2 epsilon. Okay, so what other kind of integrals you could consider for which such a formula holds? Well, first think of what are polylogs. Well, polylogs are obviously integrals of D-log forms integrated over a polytope. So there's something very special already. And in fact, you can think of this as a special case of some kind of positive geometries. So positive geometries have appeared, I think, in previous talks already on Wednesday, but let me just give you here a very hand-wavy definition of what it is, just to give you the essential. So if you can think of a positive geometry as, roughly speaking, some kind of stratified space. So space made out of, you have, say, a volume, you have faces, and it's edges for the faces, and so on. And this space comes equipped with the differential form, which has singularities precisely on the boundaries of the space. And then I also say, okay, there's some kind of recursive structure in the sense that if I now go to a boundary, like a phase of my polytope, then that phase is itself a positive geometry, and so on and so forth. And so I think you can easily see that that is similar to what you have here, right? You have polytopes which are defined by hyperplanes, and you have D-log forms which have singularities along hyperplanes. And so in the same paper where positive geometries were introduced, was also discussed that you could consider canonical integrals, they called them, which are basically take two positive geometries, you take the differential form of one and you integrate it against the other. And let's forget about all possible issues of convergence. And so those will be the kind of integrals that we want to consider, because those are probably the most natural generalizations that you can think of for polylogs, right? Okay, let's take an example. So what is kind of the simplest positive geometry you can imagine? Well, the simplest would be the point. Let's take the simplest non-trivial. We'll just say a line segment, the line segment from 0 to 1. So if this is a positive geometry, I would need the differential form with logarithmic singularities on the boundaries of this segment. The boundaries are the points 0 and 1. Well, and here's the differential form that has singularities on the boundaries at 0 and at 1. And so I have now an integration domain, and I have a differential form, so I can integrate this form over this domain. Now, of course, that by itself doesn't work because there are poles at 0, so the integral is divergent. And so that is now where dimensional regularization comes in. So we have to put some kind of factor which allows us to cure the divergence. So this is similar to dimensional regularization. Here I introduce it via some kind of toy, in a toy way. I just say I put this factor behind. Ruth will comment a bit more on where this factor comes from, well, what it means mathematically. Okay, so that is an example of an integral that we want to consider. It's an integral defined by an integration domain, which is a positive geometry, and a differential form, which is associated to positive geometry, but we also need to deform it by these factors to ensure convergence. Now, the main proposal is that if you take integrals of this type, you should be able to obtain a coaction, which is very much the same as for polylogs. So if you take an integral of some gamma, which is positive geometry, and some differential form, which comes from positive geometry, you should be able to write a formula like this. So you have to take a basis of, call it integrands, a basis of differential forms associated to geometry. if you remember Simon's talk yesterday, that goes in the direction of like a basis of the cohomological. And I also need a basis of integrands. And then in between, I need to put some kind of matrix, which is essentially, well, tells me how the basis of integrands can be paired to the basis of, contours is paired to the basis of integrands. If they were like really in one-to-one, well, dual to each other, this matrix would be the identity. Now, however, as we will see, and in particular in Ruth's talk, this matrix may not always be the identity, or not even diagonal, and then you need to include it. Here, I will not dwell on this matrix too much. I will just say that, well, an operational definition could be take a leading order in the epsilon expansion, because we're doing dimensionalization. We always consider these things as Laurent series in epsilon, and this matrix would be the leading order term. As Ruth will explain later on, this matrix is actually the matrix of intersection numbers as it has appeared yesterday already in the talks by Sebastian and Simon. Okay, good. So let's look at our example again. So that is the example that we had. This is our integral of like the positive geometry is 0, 1. The differential form is 1 that is associated to that positive geometry. And as I said, we're doing dimensional realization. So we actually look at this as an expansion in epsilon. There's a pole at epsilon equals 0 because I have these two singularities. So it's actually 2 times 1 of epsilon, 1 from each pole. And the coefficients of the expansion are zeta values. I guess those of you who are a bit familiar with these kind of integrals know that this is actually just the sum of 2 beta functions. And so if I apply the formula from the previous section, then I would say, well, the coaction of Iy, well, that is coaction of some integral of some constant gamma against the form omega. While here, the basis of forms is easy. It's just this one single form. That's all I had. I only had one positive geometry. And I only have one contour. So there's only one term in my sum of master integrals. And it gives you, of course, back the integral itself because there's nothing else. And also here, there's just this one object. But I need to take care of this matrix C minus 1. And as I said, think of it for now as the leading order term, this expansion. And so here you have 2 over epsilon, and then therefore here you need some epsilon over 2. So each of these integrals gives you back Iy, and then this factor here is epsilon over 2. Ruth will comment on it, I think, more precisely where this factor comes from. It's not so important to understand the basic concepts. Okay, so that would be the coaction on Iy. But now the question is, so what? I mean, that is, well, it's a formula, I wrote it down. It's not particularly interesting. The interesting point is the following. This is one term. But this one term represents an infinite number of terms in the Laurent expansion. And each of these terms, the coefficients, are polylogs, or they're zeta values, which are special values of polylogs. So I could have gone and computed the coaction evaluated on each of these coefficients term by term, using the coaction on polylogs that I showed at the beginning. And I show it here in the special case of zeta values. If it's odd zeta values, it gives you the zeta value tensor 1 plus 1 tensor the zeta value. If it's an even zeta value, it's just this one term here. And so this one term actually resums an infinite number of terms. And that is highly non-trivial. So there, in some sense, there are 2 different coactions at work here. One which acts on the polylogs term by term, and then the one which acts on my, call it canonical integral, my integral for positive geometry. So just give me one term, such that if you expand out this term here, you get exactly the same thing. The Laurent expansion before or after is the same. But the Laurent expansion before and then acting term by term in the expansion with delta, or expanding out this term is the same thing. And that's a highly non-trivial conjecture. And actually, Francis has talked about it last year at Amplitudes in Dublin, at least for a specific class of subintegrals, which would actually also cover this. So there is some mathematical foundation that this actually works. Okay, so, but as I said, Francis talked about it last year at Amplitudes, and he wrote a paper about where they prove it for a class of integrals with Clément Dupont. But beyond that, how much evidence do we have for the conjecture? And in the rest of the talk, I will show you more evidence, in particular, that it actually works also in the context of Feynman integrals in dimensional realization. So that there's really a way that the coaction commutes with the epsilon expansion, and there's a way to write down the coaction for the dimensionally regularized integrals. And I will talk about one-loop integrals, and then Ruth later will cover more examples. Okay, so why one-loop integrals? Well, our starting point was that we said we need positive geometries. So if you want to apply to Feynman integrals, we need somehow Feynman integrals that come from positive geometry. And that is indeed what happens for one-loop integrals. One-loop integrals, we know they all come from positive geometries. And to give you a feeling why, well, look at the one-loop box integrals. I guess that's something everybody knows very well. Let's look at this, the case where all the external legs are massless, but I put propagator masses. It's immaterial for the argument. And now let's look at the kind of the geometry associated with this. This is the Feynman parameter integral. And so the geometry corresponds to, well, where are the singular surfaces? Well, they are u equals 0 and f equals 0. And also the integration boundaries, well, they are only down here at xi equals 0. Roughly speaking. Let's forget about the delta function for a second. Okay? But the important point is that all the singular surfaces are either linear, because u is linear, or f at one loop is quadratic. So I have one quadratic and a bunch of hyperplanes. And if you take a geometry coming from something where you take, essentially, imagine a space where you take out a quadratic and a bunch of hyperplanes, that does indeed define a positive geometry. And since every one-loop Feynman integral has such a Feynman parameter representation where u is just linear, f is quadratic, every one-loop integral can be associated to a positive geometry. So the construction should apply there. Now, the other ingredient we need now is a basis of integrands, master integrals, and of contours. So let's start with the integrands, the master integrals. And there we're very lucky because at one loop, we just know a basis of master integrals. We know the basis of integrands. And it's just a well-known collection of tadpole, bubble, triangle, box, pentagon, and so on. For example, here, take any triangle integral. You know, you can always write a linear combination of a triangle or three different bubbles, one corresponding to removing, well, removing one of the three edges, or three different tadpoles, which you get by removing two edges. The only point I want to make here, it's a technical comment, it's not important for the rest, is that we choose our basis integrals to be bubbles and tadpoles in 2 dimensions, triangles and boxes in 4 dimensions, pentagons and hexagons in 6 dimensions, and so on. It's immaterial for the talk. There are technical reasons why you want to do that, but it's not so important for the rest of the talk. Okay, so that's the basis of integrands. What about the contours? Well, also there we are lucky at one loop, because the contours coming from one loop geometries have been studied in the 60s. And so let me just tell you the results. So what are the possible contours that you get from one loop geometries? Well, one is obviously just the one that we use to compute Feynman integral, right? Let's call it gamma empty. Another class of contours that you get is all possible ways of taking residues at a subset of the propagators. So gamma 1 would be the integral where I take the residue at the pole of, say, propagator 1, if I label my propagators by 1, 2, 3, 4. Gamma 1, 3 would be the contour where I take residues at propagators 1 and 3, but not at the others. And of course, we all know what the physics of that is. So taking residues at propagators means that essentially you put them on shell. So you replace propagators by delta functions, roughly speaking. So those are cut integrals. So those are the contours that compute the cut integrals. On top of that, there are other contours which correspond to taking residues at propagators, but also residues at the singularity at infinity. So those are all the contours that you can write down at one loop. Now, if you're a bit careful now and you think about what we have, so we had the basis of master integrals, which has bubbles, tadpoles, triangles, and so on. So a subset of propagators correspond to a basis of integrands. But that should, I want to have a kind of a dual basis of contours. But of course, I have way too many contours here. I do not just have subset of propagators, which would be the number 2 here, but I also have the original contour and I have all those where I take the singularity as infinity. So I seem to have way too many contours to get any kind of duality. So there must be relations among the contours. And also those have been, well, some have been classified. In particular, this one here. So that's the relation that was known from the 60s, which says that whenever you have a contour where you take a singularity at infinity, is this just a linear combination of contours where you do not take the singularity at infinity. So every cut of a singularity at infinity, let's put it like that, so taking a resident infinity, I can always write as a linear combination of other integrals. And there's this factor of 2 in this relation. The others come with factor of 1. And this will be important later on. So that allows me to eliminate all contours that have infinity. In addition, there's the following relation, which says that the original integral, so my original Feynman integral, n meaning just numbers of propagators, is just always the sum of all single cuts and all double cuts up to a power of epsilon, and up to powers of pi, depending on what is the branch on which you compute these cuts. So the sum of all single and double cuts reproduces the full integral. That is always true. So this allows me also to, if I go back, so the last relation allows me to eliminate this contour. The first relation allows me to eliminate all those that take a residue in infinity. So I only have as independent contours those that correspond to a subset of propagators, which are precisely in one-to-one correspondence to my master integrals. And so what you get is the following. So what is, for example, the coaction on a triangle integral? You get now, well, this is a triangle integral where the propagators are massless and the external legs are off-shell. So the master integrals include the triangle and 3 different bubbles. There are no tadpoles because propagators are massless. And you get the following relations. So you have now a linear combination of terms where you have the master integrals in the first factor, the bubbles in the triangle, and the integrals over the contours where you take residues at the poles of the propagator, so cut integrals in the second integral. And so those are nice pictures, but what is really highly non-trivial is that each of these pictures represents an infinite series in dimensional regularization. And again, the statement is that if you take the triangle integral and you act with to get an infinite series with coefficients that are polylogs, you compute the coaction of every polylog individually. That is the same as if you stick in these expansions here and you expand out the different terms of this coaction. So it's a highly non-trivial statement. We've checked this explicitly up to weight 4, because at some point you run out of steam. Ruth will tell you a bit how you can think about it all orders and epsilon. That's the first thing I want to say. So it's a highly non-trivial statement that the Laurent expansion commutes with the correction. The second thing is the following. So what you see here, you see some structure. So for example, this integral here, which has 2 propagators, call them E1 and E2, is paired to the triangle where you cut precisely these 2 propagators. And that goes on like that. So this one has propagators E3, E2, E3. In the other side, you have the cuts of E2 and E3. And so on, E1, E3, E1, E3, and here the triangle itself is associated with triple cut. So there's really a structure in how this coaction organizes. It's really that you pair always the first factor a master integral with the corresponding cut. And the last thing which I want you to appreciate is the following. This integral is finite. Because all the external legs are massive, this thing is finite. These things are divergent. They start with 1 over epsilon. So you would think, well, how can this ever be true? And the reason is that there is this relation that says, well, the sum of all double cuts in this case, there are no single cuts, they all vanish because propagators are massless, is equal to the full integral up to another epsilon. And you see that all these bubbles have the same pole. So the coefficient of the pole is just the sum of all the double cuts, which are proportional to epsilon times something finite. So the poles cancel. So there's really a very intricate interplay between the way the contours organize, the relations between the contours, and the fact that this coaction works order by order in epsilon. Okay, so let's look at another example. So this is simple. This is a bubble now with massive propagators. So as we said before, you take now the bubble. So the bubble itself should come with the integral where you cut the 2 propagators that correspond to the bubble. You have the tadpole. Now you only cut 1 propagator, the one that corresponds to the propagator, the tadpole, and the third one. this equation is wrong. And however, if you play a bit, you realize that the following relation holds. So this term is, the first term is the same. So the bubble comes with the double cut of the bubble. The tadpole, however, comes with the single cut plus 1/2 the double cut. So what is going on? So it looks like you're kind of just readjusting things so they come out right. The reason is there was this relation between residues at infinity that you can always remove. And I said there's a factor of 2 which will play a role. Because if you pull out this factor of 2, you see that the contour where you take the residue at infinity and at the first propagator is just the same as the contour where you take the single cut plus 1/2 the double cut. And that is precisely what you see here. So this combination is not random. This combination really is dictated by the form of the double cuts. So it tells you in some sense that the contour that is dual to the tadpole is not a single cut, but it's a single cut and the residue at infinity. Okay, and if you go through it, you actually arrive at the following very simple and beautiful formula. So GC is a one-loop graph. C is a subset of propagators that you would consider cut. Then the coaction can really always be written in a very compact form that fits in a line, which is just purely combinatorial. So you sum of all possible ways of taking out, well, of pinching propagators on one hand. Gx means it's the graph G where you pinch a subset X of propagators. And on the other side, you put the same graph where you cut the propagators X. And well, there are sometimes these factors of 1/2 that you have to add, depending on whether the number of cuts is even or odd. And I should mention that recently, Matija Tapuskovic has proven some motivic version of this formula for finite triangles and box integrals in 4 dimensions. Not in dimensionalization, but in 4 dimensions. This formula was proved wrong. But we observe that it holds in all cases, and there's some motivation when you look at like the contours and how the contours correspond to that. Okay, just to show you that things get really non-trivial, and the fact that the correct commutes with dimensional organization, it's expansion Epsilon, is non-trivial. This is an identity that holds. If you compute this box with one massive propagator, and so you can expand it in DimRec, you get polylogs, you act with the correction of the polylogs order by order. That is the same as this particular thing here. We have tadpoles and paired with single cuts of the box, and bubbles with massive edges, triangles with massive edges. And if you expand each of these things in DimRec, you get exactly the same as if you had computed the correction order by order on this side. Okay. And in the last couple of minutes, so how much time do we have left, David?
Nominally -2 minutes, but since we actually running a little bit ahead of schedule, please just go ahead.
Okay, I have 3 slides, so good. So let me just quickly mention 2 applications. One is you can easily get differential equations. So in particular, so whenever you have the correction, you can read off the differential equation. And I show it here, for example, for a pentagon. There are sums of all possible ways of pinching edges. But one of the interesting things is that since the correction tells you pair master integrals with cuts, it tells you that the d logs that appear in the integral, in the differential equation, they are just certain cuts of the integral, or leading orders of these cuts. So you compute this cut, which is triple cut of the pentagon, to leading order in epsilon, that's a log. Well, d of this log will be the coefficient of the triangle, obviously. And the amazing thing is that when you look at this formula, since it can only be logs, there are only very few cuts that give you logs, because if you put here an octagon would be a weight 4 function. So you need to take many cuts. And you can actually check that whatever enters the differential equation are maximal, next to maximal, by which I mean maximal means all propagators are cut. Next to maximal means all but one propagator is cut. Next to maximal, all but 2 propagators are cut. Those are the only ones that enter the differential equation. And only to leading order in epsilon, where they are logs, except for the maximum cut, but let's discuss that. And those are things you can even compute for arbitrary numbers of scales, arbitrary number of edges, arbitrary number of masses. They're just closed formulas for these guys. So you can really write down the differential equations for all one-loop integrals in closed form. You know them all. There are formulas where you just need to, well, you have some certain gram determinants that's in these logs, and that's it. I think it would be interesting to figure out how this matches to what Simon said yesterday about differential equation and dual of Feynman integrals. But that's, of course, not for this talk. Now, of course, as soon as you have differential equations in D-log form, you can get symbols. So in particular, you can solve them and you can realize that, for example, the symbol of the triangle is just made up to say to order epsilon 0. All the pictures are now order epsilon 0 because this is a symbol of the expansion in epsilon. So the symbol of the triangle would have in the first factor bubbles, and the second factor cuts of bubbles. This is a way two functions, so the symbol just have two entries. And there would be tadpoles, meaning logs of masses in the first entry, with single and double cuts of the triangles. The symbol of the box is logs coming from bubbles, and double cuts of boxes. Hexagons would have, that's the way, three functions in 6 dimensions, so that has bubbles, and then always double cuts of boxes, quadruple cuts of hexagons, and you can easily see how this goes on. And again, the things that enter here, you can really compute them once and for all. They're closed formulas, so you can really write down the symbols of all one-loop integrals in closed form. And one thing I want to highlight here is that you see this formula looks much more complicated than this. That is because these integrals are dual conformally invariant in 4 and 6 dimensions respectively. And so the symbol entries are just the corresponding dual conformally invariant integrals, while the triangle is not, and that therefore it has more terms because you can also have the non-conformally invariant integrals. For example, also I skipped here the pentagon on purpose because pentagon is also not dual conformally invariant in 6 dimensions. And so its symbol would have bubbles, double cuts of boxes, quadruple cuts of pentagons, but then you also have tadpole terms, triangle cuts that come in the second entry, pentagons cuts that come in the third entry, and so on. But again, you can really write down these symbols for arbitrary number of scales, external legs. They are just, you can just write them down in closed form. Okay, but that brings me to the end. I both have convinced you there's strong evidence that there's a coaction which acts in integrals associated to positive geometries, and which is consistent with the expansion dim reg. So if you kind of regulate your positive geometry integrals in dim reg, expanding in epsilon, then computing the coaction, or applying this formula for the coaction that's shown you is the same thing. And this can even be proven, or was proven already in some cases rigorously. Ruth may mention that in the work by Brown and Dupont. And I also discussed what you get at one loop, where every integral is associated with positive geometry. And there's, I think, a very non-trivial interplay between the cuts and the contours and what you need, for example, to get the poles to cancel, to get the right base of contours. And you can really use it also for something practical, like getting the symbols of all one-loop integrals and getting the differential equations for all one-loop integrals in closed form. And that was the story in one loop. And so now I think Ruth will continue, and she will tell you a bit more about other classes of integrals where you can apply it, and also some first examples of two-loop integrals. Thank you very much.
Thank you, Claude. Let's actually have a live round of applause. And before we go on, there's one question here. And if I may also ask Claude to stay around and be available for questions after Ruth's talk, since that there may be questions that arise later. So let's start with Nima.
Hey, Claude, a beautiful talk. It's really cool that the coaction commutes with dim reg. That actually made me wonder something. Recently, I've been enjoying looking at I think what's called analytic regularization. I forget the name, but it's what you get if when you go to Feynman parameter space, you put some fractional power for all of the Schwinger parameters or some fractional powers in the propagators. Do you expect that? So that's kind of like dim reg, except there are many epsilons, one for each propagator. Do you think something like this would extend to that case? Have you thought about it at all?
Yes, analytic regularization. Now, you always need to expand around something. And so whatever I say is expanding around integers. So if you try to expand around a half, I wouldn't know What's
No, no,
going
no.
on?
I mean expand around integers. Except in analytic regulation, there are many epsilons rather than just one
Okay.
overall epsilon. That's
Okay.
what I was wondering.
Okay, then we're on the same page. And the answer is yes. And actually, so I mentioned here the work by Brown and Dupont. So what they looked at is one-fold integrals, Lauricella functions, but essentially integrals of x minus something raised to some arbitrary power. And they show that the coaction commutes with the expansion in these parameters at integer places, roughly speaking. So that is like having arbitrary epsilons for every possible propagator. Yeah, so the answer is yes. I would expect it to hold.
Simon?
Yeah, hi, yeah. Nice talk, thanks, Claude. I'd like to have a question and comment about the role of integration contours in this story. Just trying to make sure, yeah, because if we're looking for coaction, and not a coproduct, as far as I understand, the integration contour stays on the left of the tensor product, but on the right, you only have, on the right of the tensor product, it's really pairing with forms, right?
Yes.
Yes. So this is where one can ask, where does the dual form that we discussed, that I discussed yesterday fit in this story? And of course, the pairing between dual forms and form that I described yesterday is algebraic. So it's not the thing you have on the right of the product. But a natural candidate is you take the complex conjugate of the dual forms and get some kind of single valued integral. So I don't know if you have looked at any such possibility or.
No, but so I fully agree with what you said. So I agree with 100% with everything. So the thing on the right, you should think of it as a single valued version of the integral. And actually, I mentioned only at the beginning that the things on the right hand side, there's a subtlety there, the RAM objects. And actually, for us, they're defined up to I pi. So there's at some point the mod I pi, which indeed, when you do make single valued, all these I pi's, which come from discontinuities, go away. Now, you can think of it what you see here as, imagine you had used single valued version. So take log x, the single valued version is log mod x squared, but now only keep the holomorphic part in some way, okay? That is the thing that you see here. Then what you say about using the dual form and the complex conjugate, that is, well, maybe Francis would be the right person to ask for the details, but my understanding is that that is precisely what it is. So if you take the dual form, complex conjugated, wedge it with the other form, integrate over the whole space, that should be the single valued version of some RAM object, at least to my understanding from some other paper by Brown and Dupont, the one on the string amplitudes. And that would be the more natural object that can sit on the right-hand side. Well, that is the correct object. And then you should actually be able to go beyond everything that is, say, what we call now positive geometries or polylogs, then you could go much further.
Yeah, okay, thanks for that. It would be interesting to find calculation to check that. That's very nice. But yeah, because the experience is that classifying these dual forms is somehow, it's algebraic, so it's somehow much easier than classifying these contours. So that could be helpful for that. Yeah. Thanks.
Okay.
Oliver?
Hi. This is an extension of Claude's answer to Nima's question. What about situation with multiple epsilons? So in string theory, open string tree-level amplitudes, similar integrals appear where epsilon is replaced by alpha prime, more precisely alpha prime dressed with the Mandelstam invariance. So for each Mandelstam invariant, there's a separate epsilon. And such coaction formula have been written down for endpoint open string tree amplitudes. So it's partially work with myself and Stefan Schneeberger and partially James Drummond and Eric Ragusi, who also clarified a connection to the Drinfeld associator. So in summary, such formula work with a large number of different epsilons.
Yorgos?
Yes, can you hear me?
Yes, we can hear you.
Hi, Claude. Hi, everyone. Very nice talk. And perhaps it's a naive question, but some of the integrals, of course, comes with rational pieces, not just transcendental. These completely commute through the coaction, or what do you do with those?
Yeah, so good point. So that's a very important question. Remember that here I said we choose as the basis of integrals those guys. Those are precisely the one which have exactly one leading singularity, and you normalize it away, and then it's pure. So that means that you can find at one loop easily find a basis where say, oh well, let me not this formula here, where all these guys are pure functions. So those don't have them. I choose a basis where everything is pure. Now, of course, the original integral may have had the rational pieces.
Exactly. That's why I wondered, because you showed some boxes, some massless hexagons, and so on, and these have.
Correct. Now, but you see, omega is linear in omega. So everything, those just go through, because omega itself would be a linear combination of these pure functions. I would act with the coaction on these pure functions, and then you see they recombine into the same omega on this side. So they really commute through. The trick is that here, this guy is a basis of pure guys, and all the other algebraic or rational factors would commute through and would recombine into the same integrand omega, that would give you all the non-pure stuff as well.
Okay, that makes sense. Thanks.
Lance?
Hi, Claude. Nice talk. Hey. I guess we had a differential equation for one loop integrals back in '92, and it related the first derivative of an endpoint integral to the same topology and integrals with one canceled propagator or one lower point. Whereas yours also seems to have two lower propagators. I wondered if you'd looked at the relations between those equations.
No, but I think simply because we may not have known it. So maybe if you can send me the reference, then we could check what exactly the relation is. So from the top of my head.
Sure. It's in your papers, the reference, but I'll send it to you. Yeah.
Okay, thanks.
Give Claude another round of live applause.